Okay, good morning. Yes, I would like to present you our paper with the name A Virtual Analog Model of a EDP Voltage Controlled Filter. Short outline. So first I give a brief introduction about the device and a bit of history and so on. And then we do a bit of circuit analysis and small signal analysis just to get a brief understanding how the circuit is working in general. And then we go on with the main part, which is modeling of the nonlinear circuit components. And then we take a look at the results and conclude. So you see the WASP synthesizer, which is on the left-hand side. This is a two-oscillator monophonic synthesizer, and it was released in 1978. Yes, by Adrian Wagner and Chris Huggett. These are the co-founders of EDP. And what's interesting about this circuit at this time was that it was only listed for about £200. So this is half the price if you compare this with synthesizers of the era like the Moog or Korg or something like this. And this price was mostly due to some compromises in design, which were, for example, it has a really cheap plastic enclosure and no mechanical keyboard, just a touch-sensitive thing. And also the electronic design used some, I guess at this point, very new concepts to get special sounds, but also reduce the price. And what we actually modeled in this work was the WASP filter. And this is one compartment here of this synthesizer, it's the filter. And we actually modeled the Doppler version on the right-hand side because nowadays it's really tough to get hands on an original WASP filter. They go about €2,000. So, and this WASP filter from Köper is about 100. So, okay, let's take a look at the basic layout of a circuit. So basically, it's a second-order state variable filter, which you can see in Figure A. So we have a simultaneous high-pass, band-pass, and low-pass output, and this is done with two integrator blocks and two feedback paths, and everything is then summed up at the input. And let's take a brief look how this is integrated in the circuit. So this is just one integrator. So this is an ideal form, just using an op-amp and a resistor and a capacitor. But of course, this filter is a voltage-controlled filter, so that means we want to somehow get the cutoff frequency dependent on some control voltage or control current. And this can be done by using so-called operational transconductance amplifier. So we have a differential input voltage, and the output current can be controlled by this bias current. So that means basically we can change the value of this resistor with bias current. And of course, this introduced nonlinearity to a circuit because the OTA is by nature a nonlinear device. And what is also kind of unique with WASP filter design is that it doesn't use operational amplifiers, but CMOS inverters instead. And at the time being, it was, I can only guess, mostly due to the price, because a CMOS inverter can be built with just two transistors, whereas the operational amplifier needs way more. Okay, then let's take a brief look at the circuit schematic. This is only the signal path, so there's also a part about the bias generation and so on. So we can see the building blocks from the slide before. So this is the first integrator consisting of OTA and followed up by a CMOS inverter, and then we have a second integrator block here, and we see we have a feedback path here and the feedback network here. The difference to the ideal representation we saw before is that we now have also capacitance here in this feedback path, and this is also nonlinear and has also 2 capacitors. Maybe you don't need to count this one, but you get the point. But let's first start with some small signal analysis to see how the state variable filter is actually working. So with this, we assume we use a linear integrator. We will later change this to a nonlinear model. So this means we have just a negative integral of the input voltage over C in respect to time. And we have a linear OTA. It means we can control the output current of the OTA with a bias current, and then multiply this by the differential input voltage over 2 times the thermal voltage. And in the small signal analysis, we just say, okay, with diodes are of no interest because we have just so small voltages. And yeah, first finding, I will give no derivation for this here because it would take too long. But you can see with these 3 transfer functions the behavior of this state variable filter. So see the high pass has a square term in the denominator when we have only S, and then only the cutoff frequency left for the low pass filter. And you also notice that the denominator is the same for each filter. And if we would compare this to a linear and common state variable filter of second order, when you would see these transfer function H1 of S and H2 of S would be constants. And in this case, they represent the feedback network. So H1 of S is basically this path here, first feedback path from below pass, and then we have H2, this is the feedback path from the bandpass output. And what we could find is that for a low resonance setting and a high cutoff frequency, we can basically use this linear approximation in a certain extent. So that means for these settings, we can set this transfer function as a constant and just have a normal linear state variable filter. But yeah, most of this the sounds and the circuit design is best modeled if we take a look at the nonlinear parts. And we start with a CMOS inverter model, which we just modeled by using the 2 internal MOSFET it comprises. So we did measurements of these MOSFETs and then optimized it with CMOS with an NMOS and PMOS channel MOSFET. I won't give a model here because it's basically in a DAFx paper from 2 years from me and Martin Holters. But I will give the results. So this is the optimized CMOS inverter. You can see the measurement in black, and the dashed line is the model. Okay, there's a tiny gap here at the bottom, but actually this is in the range of production deviations, so that's actually not a big problem. Pretty simple, but works really fine. And when we take a look at VOTA, so the transconductance amplifier, you can see in this plot the output current against the input voltage. And here you see, okay, if we would take a linear model, then we can only model this area here near the origin. We, of course, need to somehow model the saturation effect. And this can be simply done by just using a hyperbolic tangent function. And what we also did is we scaled it with parameter alpha, which controls the height of these saturation regions. And then better, it's just controlling the slope. So this works pretty well, not very complicated. But there's one thing about the OTA we need to take a look at, which is really important for modeling this filter. We will see later. And you can see, again, the output current of the OTA, and now against the output voltage. So what we did here is just we put a load at the output and then sweep the output voltage from 0 to the supply range. So this was 12 volts. And what you would expect if you take a look at the model from the previous slide, then you would expect a set of straight lines because it's, of course, independent of the output voltage. But we have these jumps here near the supply rails, which is also common for operation amplifiers and some devices like this. But we'll see this is really important and crucial to model these jumps and saturations effects to get a faithful representation of the filter. You can also see the results here. Let's take a look at the model. So we define 3 auxiliary functions, and the first one being the function we saw before with just modeling the input behavior, so nothing new here. And then we have 2 other functions, FH and FL, which model the transition from these plateau levels to the normal operating area. So, FH is then for the high voltages and FL for the low voltages. And yes, actually these parameters H and L are just the height of the plateau. And when you see the transition is modeled again by hyperbolic tangent, and we have a parameter for the steepness and for the actual position in respect to the output voltage. And then we can simply get our output current by adding all these functions up. And the nice thing is they don't influence each other in their operating region. So that means this input behavior is kept as it was. So we have this perfect match regarding the input voltage, but we also can model these jumps if we take a look at the output voltage. So let's take a look at a few results. This is only a snapshot. If you want to get a more detailed view, then please take a look at the paper. So what we did here is we had a sine sweep input, and this was starting from low frequencies and then reach the maximum frequency in the middle, and then we go from high frequency again to low. And what you see here is the bandpass output. So you see the bandpass shape here. And the setting for filter was the resonance was at 20%. That means the feedback path we saw in the beginning, relatively low feedback. And where we see, okay, this simple OTA model, not modeling this output behavior, just performs similar to the extended model. And what you also can see here, so the black waveform is the measurement, the model, and the red one is the measurement, so the envelope of a measurement, basically. And you see, okay, we behave a bit differently, but very close to the measurements. But if you now take a look, what happens if we increase the resonance, so if we increase the nonlinearity, when we see, okay, the simple model is just not working at all, so we have some clipping effect, and we also have a shift of cutoff frequency, and it's just not following the shape of the measurements at all. Whereas the extended model, modeling this output behavior, just follows the measurements quite nicely. So it was only a snapshot of the results, but you have not much time left to give you a more detailed view on this. So to conclude, The extended OTA model and the CMOS inverter models allow us a faithful digital representation of the WASP filter. And yes, they behave precisely in the optimization range, but we also need to take care to use these models only in the range of the measurements we did before, because we can introduce energy to the circuit if we do not do this. Yes, and of course it's helpful to measure all the components prior to assembly, which we could not do, but this would increase accuracy. Okay, so then thank you. And yeah.
Any questions?
I have noticed that with that specific dope for WASP filter module, certain combinations of resonance and input level and frequency can give some chaotic output. Have you noticed that with your model? Have you been able to reproduce that?
Yeah, no, I was not able to reproduce it. So we could produce some self-oscillating stuff with the WASP filter itself, but it's really hard to get this combination of knob tuning into the model. So because basically it's not only one setting, but you need to tune right and then left again in a certain way to produce some of these sounds. So I think it's possible, but it's really hard to program this. Yeah.